In mathematics, a vector bundle is a topological construction that makes precise the idea of a family of vector spaces parameterized by another space X. To every point X of the space X we associate a vector space V in such a way that these vector spaces fit together to form another space of the same kind as X, which is then called a vector bundle over X. The simplest example is the case that the family of vector spaces is constant, i.e., there is a fixed vector space V such that V equals V for all X in X. In this case there is a copy of V for each X in X, and these copies fit together to form the vector bundle X times V over X. Such vector bundles are said to be trivial. A more complicated class of examples are the tangent bundles of smooth manifolds. To every point of such a manifold we attach the tangent space to the manifold at that point. Tangent bundles are not, in general, trivial bundles. For example, the tangent bundle of the sphere is non-trivial by the hairy ball theorem. In general, a manifold is said to be parallelizable if and only if its tangent bundle is trivial. Vector bundles are almost always required to be locally trivial, however, which means they are examples of fiber bundles. Also, the vector spaces are usually required to be over the real or complex numbers, in which case the vector bundle is said to be a real or complex vector bundle. Complex vector bundles can be viewed as real vector bundles with additional structure. In the following, we focus on real vector bundles in the category of topological spaces. Definition and first consequences. A real vector bundle consists of topological spaces X and E, a continuous surjection pi, Ex. For every X in X, the structure of a finite-dimensional real vector space on the fiber pi-1, where the following compatibility condition is satisfied. The map is a linear isomorphism between the vector spaces Rk and pi-1. The open neighborhood U together with the homeomorphism phi is called a local trivialization of the vector bundle. The local trivialization shows that locally the map pi looks like the projection of U times Rk on U. Every fiber pi-1 is a finite-dimensional real vector space and hence has a dimension kx. The local trivializations show that the function xkx is locally constant, and is therefore constant on each connected component of x. If kx is equal to a constant k on all of x, then k is called the rank of the vector bundle, and E is said to be a vector bundle of rank k. Often the definition of a vector bundle includes that the rank is well defined, so that kx is constant. Vector bundles of rank 1 are called line bundles, while those of rank 2 are less commonly called plane bundles. The Cartesian product x times Rk, equipped with the projection x times Rkx, is called the trivial bundle of rank k over x. Transition functions given a vector bundle Ex of rank k, and a pair of neighborhoods U and V over which the bundle trivializes via the composite function is well defined on the overlap, and satisfies for some GL-valued function. These are called the transition functions of the vector bundle. The set of transition functions forms a Chekhov cycle in the sense that for all U, V, W over which the bundle trivializes, thus the data defines a fiber bundle, the additional data of the GUV specifies a GL structure group in which the action on the fiber is the standard action of GL. Conversely, given a fiber bundle with a GL cocycle acting in the standard way on the fiber Rk, there is associated a vector bundle. This is sometimes taken as the definition of a vector bundle. Vector bundle morphisms. A morphism from the vector bundle pi1, E1x1 to the vector bundle pi2, E2x2 is given by a pair of continuous maps F, E1, E2 and G, x1, x2 such that G pi1 equals pi2 F. For every x in x1, the map pi1 minus 1 pi2 minus 1 induced by F is a linear map between vector spaces. Note that G is determined by F, and F is then said to cover G. The class of all vector bundles together with bundle morphisms forms a category. restricting to vector bundles for which the spaces are manifolds and smooth bundle morphisms, we obtain the category of smooth vector bundles. Vector bundle morphisms are a special case of the notion of a bundle map between fiber bundles, and are also often called bundle homomorphisms. A bundle homomorphism from E1 to E2 with an inverse which is also a bundle homomorphism is called a bundle isomorphism, and then E1 and E2 are said to be isomorphic vector bundles. An isomorphism of a vector bundle E over X with the trivial bundle is called a trivialization of E, and E is then said to be trivial. The definition of a vector bundle shows that in any vector bundle is locally trivial. We can also consider the category of all vector bundles over a fixed space X. As morphisms in this category, we take those morphisms of vector bundles whose map on the base space is the identity map on X. That is, bundle morphisms for which the following diagram commutes. A vector bundle morphism between vector bundles pi1, e1x1 and pi2, e2x2 covering a map G from x1 to x2 can also be viewed as a vector bundle morphism over x1 from e1 to the pullback bundle G*e2, sections and locally free sheaves. Given a vector bundle pi, ex and an open subset U of X, we can consider sections of pi on U, i.e., continuous functions S, UE where the composite pi S is such that equals U for all U in U. Essentially, a section assigns to every point of U a vector from the attached vector space, in a continuous manner. As an example, sections of the tangent bundle of a differential manifold nothing but vector fields on that manifold. Let F be the set of all sections on U. F always contains at least one element, namely the zero section. The function S that maps every element X of U to the zero element of the vector space by -1. With the pointwise addition and scalar multiplication of sections, F becomes itself a real vector space. The collection of these vector spaces is a sheaf of vector spaces on X. If S is an element of F and alpha UR is a continuous map, then alpha S is in F. We see that F is a module over the ring of continuous real-valued functions on U. Furthermore, if Ox denotes the structure or sheaf of continuous real-valued functions on X, then F becomes a sheaf of Ox modules. Not every sheaf of Ox modules arises in this fashion from a vector bundle. Only the locally free ones do. Even more, the category of real vector bundles on X is equivalent to the category of locally free and finitely generated sheaves of Ox modules. So we can think of the category of real vector bundles on X as sitting inside the category of sheaves of Ox modules. This latter category is abelian. So this is where we can compute kernels and co-kernels of morphisms of vector bundles. Note that a rank n vector bundle is trivial if and only if it has n linearly independent global sections. Operations on vector bundles. Most operations on vector spaces can be extended to vector bundles by performing the vector space operation fiberwise. Formally, E** can be defined as the set of pairs where XX and phi*. The dual bundle is locally trivial because the dual space of the inverse of a local trivialization of E is a local trivialization of E**. The key point here is that the operation of taking the dual vector space is functorial. There are many functorial operations which can be performed on pairs of vector spaces, and these extend straightforwardly to pairs of vector bundles E, F on X. A few examples follow. The Whitney sum or direct sum bundle of E and F is a vector bundle EF over X whose fiber over X is the direct sum XFX of the vector spaces X and Fx. The tensor product bundle EF is defined in a similar way, using fiberwise tensor product of vector spaces. The Hom bundle Hom is a vector bundle whose fiber at X is the space of linear maps from X to Fx or L. The Hom bundle is so called because there is a bijection between vector bundle homomorphisms from E to F over X and sections of Hom over X. Building on the previous example, given a section S of an endomorphism bundle Hom and a function F, XR. One can construct an eigenbundle by taking the fiber over a point XX to be the F eigenspace of the linear map S, XX. Though this construction is natural, unless e.g.a is taken, the resulting object won't have local trivializations. Consider the case of S being the zero section in F having isolated zeros. The fiber over these zeros in the resulting eigenbundle will be isomorphic to the fiber over them in E, while everywhere else the fiber is the trivial zero-dimensional vector space. The dual vector bundle E** is the hombundle homomorphisms of E and the trivial bundle R times X. There is a canonical vector bundle isomorphism hom equals E** F. Each of these operations is a particular example of a general feature of bundles. That many operations that can be performed on the category of vector spaces can also be performed on the category of vector bundles in a functorial manner. This is made precise in the language of smooth functors. An operation of a different nature is the pullback bundle construction. Given a vector bundle EY and a continuous map F, XY, one can pull back E to a vector bundle F** E over X. The fiber over a point XX is essentially just the fiber over FY. Hence, Whitney summing EF can be defined as the pullback bundle of the diagonal map from X to XXX, where the bundle over XXX is EXF. Remark: let X be a compact space. Any vector bundle E over X is a direct summand of a trivial bundle, i.e., there exists a bundle E, such that E is trivial. This fails if X is not compact. For example, the tautological line bundle over the infinite real projective space does not have this property. Additional structures and generalizations. Vector bundles are often given more structure. For instance, vector bundles may be equipped with a vector bundle metric. Usually this metric is required to be positive definite, in which case each fiber of E becomes a Euclidean space. A vector bundle with a complex structure corresponds to a complex vector bundle, which may also be obtained by replacing real vector spaces in the definition with complex ones and requiring that all mappings be complex linear in the fibers. More generally, one can typically understand the additional structure imposed on a vector bundle in terms of the resulting reduction of the structure group of a bundle. Vector bundles over more general topological fields may also be used. If instead of a finite-dimensional vector space, if the fiber F is taken to be a Banach space, then a Banach bundle is obtained. Specifically, one must require that the local trivializations are Banach space isomorphisms on each of the fibers and that, furthermore, the transitions are continuous mappings of Banach manifolds. In the corresponding theory for CP bundles, all mappings are required to be CP. Vector bundles are special fiber bundles, those whose fibers are vector spaces and whose cocycle respects the vector space structure. More general fiber bundles can be constructed in which the fiber may have other structures, for example sphere bundles are fibered by spheres. Smooth vector bundles. A vector bundle is smooth if E and M are smooth manifolds. P.E.M. is a smooth map, and the local trivializations are diffeomorphisms. Depending on the required degree of smoothness, there are different corresponding notions of CP bundles. Infinitely differentiable C-infinity bundles and real analytic C-omega bundles. In this section we will concentrate on C-infinity bundles. The most important example of a C-infinity vector bundle is the tangent bundle of a C-infinity manifold M. The C-infinity vector bundles have a very important property not shared by more general C-infinity fiber bundles. Namely, the tangent space TV at any Vx can be naturally identified with the fiber X itself. The identification is obtained through the vertical lift VLV. XTV, defined as the vertical lift, can also be seen as a natural C-infinity vector bundle isomorphism P***EVE, whereas the pullback bundle of over E through P, EM, and VE equals e.g.a is the vertical tangent bundle, a natural vector subbundle of the tangent bundle of the total space E. The slit vector bundle E0, obtained by removing the 0 section 0e, carries a natural vector field VV equals VLVV, known as the canonical vector field. More formally, V is a smooth section of, and it can also be defined as the infinitesimal generator of the Lie group action for any smooth vector bundle. The total space T of its tangent bundle has a natural secondary vector bundle structure, where P** is the push-forward of the canonical projection P.em. The vector bundle operations in this secondary vector bundle structure are the push-forwards plus asterisk T and lambda asterisk T of the original addition plus E times E and scalar multiplication lambda E. K-theory. The K-theory group K of a manifold is defined as the abelian group generated by isomorphism classes E of complex vector bundles modulo the relation that whenever we have an exact sequence, then in topological K-theory. Co-theory is a version of this construction which considers real vector bundles. K-theory with compact supports can also be defined, as well as higher K-theory groups. The famous periodicity theorem of Raoul-Bott asserts that the K-theory of any space X is isomorphic to that of the S2X, the double suspension of X. In algebraic geometry, one considers the K-theory groups consisting of coherent sheaves on a scheme X, as well as the K-theory groups of vector bundles on the scheme with the above equivalence relation. The two constructs are the same provided that the underlying scheme is smooth.